Yes, good evening, everyone. Am I audible? Please let me know in the chat box so that we can start our session. Please let me know in the chat box whether am I audible. Okay, great. Thanks for the confirmation. So yeah, so welcome to UART-based controller workshop. This is day one. Now, before going to start this particular session, I wanted to just brief it up, like what is exactly we are going to learn in this particular workshop and what are the requirements and what is outcomes of this particular workshop and all, right? Yes. So first of all, we are going to look into UART protocol. That is very important. Without understanding UART protocol, how can we do this particular workshop or how can we do this project, right? So obviously, UART protocol is mandatory and requirement. Okay. So we are just going to look into what is this UART protocol. That will be like a small session, a brief intro about the things that it will be clear. Okay. Now, can I know how many of you know UART protocol in prior, or how many of you don't know? If you know about UART protocol, just type yes, or if you don't know about UART protocol, just type no. So that I will just come to know how many of you know UART protocol or how many of you don't know UART protocol. Okay. Okay, not an issue if you don't know about UART protocol. If you know UART protocol, not an issue. Anyways, we are going to just cover it out so that it will be clear about the project, right? Now, and one more prerequisite is one prerequisite of this particular workshop is you need to know about UART protocol, and the second prerequisite is you need to know Verilog coding. And I hope everyone knows Verilog coding, right? So if you don't know, I recommend you to once please go through Verilog programming. So if there are any people who are not aware of anything about Verilog programming, I recommend you to please go through it. Okay, right. So let us try to understand what is it. First of all, we are going to learn in this particular project. Let me give you intro about our project. Then we will start with uh, explaining the things and all. Okay. First of all, before that, please let me know whether my screen is visible. Please let me know my screen visibility. Okay, that's great. So let's try to have this particular session interactive so that we can have it for a long time. So let's say if no one is responding or your energy is low, then we will wrap up it in less time. Or else, if your energy is high and if you are wanted to learn more, then we can have it for a longer time, right? Yes. So coming to this particular UART-based LED controller, the workshop is very simple. We are going to have an LED, okay, and that particular LED we are going to control it. Okay. Now, what do I mean by this controlling? Let me show you one simpler animation kind of thing. Yeah, this HTML file. Let me show you. So this is one application. Okay. Some user has developed some kind of application. Okay. Now before that, I'm going to use FPGA board. I'm not going to have any physical FPGA board, but if anyone has that particular physical FPGA board, they can just work on this. So what is the FPGA board we are going to use? Is we are going to use Nexus board. I've written this particular coding constraints and all with respect to this particular Nexus board. So this is my actual board, and on this particular board, there are several LEDs which are present over here. You can see, right? So we are going to basically control this particular LEDs. Whatever the application is there, right? This particular user interface application is there, right? This application need to control this particular LED. Okay. Now, what do I mean by this controlling LED? So in this HTML, if you can see, first of all, user is selecting LED 0 to LED 4. That means user has five options from 0 to 4. That means let's say user is having access to this 1, 2, 3, 4, 5. First five LED access user has access. Okay. So I will let you know how user can get access to this particular LEDs, how we are going to give him access and all. I will explain you. Okay. Just for now, let's say user has access to this five LEDs. Okay. Now what is user is going to do? User is going to select LED 0, and let's say if he is basically selecting static. Okay. And if it's increasing the brightness, the LED should be glowing at its maximum higher level. So I mean, this particular LED is selected and that particular LED should glow. Okay. And let's say if the brightness is decreased, then the physical LED which is present on the board, right, that should be completely turned off. Okay, that is my requirement. Okay, the user is going to have control of this. Let's say if the brightness is more, and if he's selecting this fade in the sense, LED will be glowing and it will be turning off, fading. Okay, so for some time it will be on, sometime it will be off. So that particular thing should be implemented on this particular physical LED on my particular board. Okay. Now, next configuration is blinking. That means it should blink. Whatever the LED is there, right? That should blink. And we can also adjust the brightness. Okay. So if the user is dealing with this particular application, if he's doing it in this particular application in his particular PC, then that should be reflecting on his particular hardware. That is my entire project. And what we are going to implement is we are not going to actually implement it on the hardware because I don't have a physical hardware with me. Okay, but I will show you how this can be implemented onto a physical hardware. Okay, that you can implement if you have a physical hardware with you. Okay, this is what we are going to do. This is our project. So the project, is it clear for everyone? Please let me know in the chat box. The project requirements, are they clear? Okay, anyone having any queries with the project requirement? Okay, that's great. That's great. Hope the project requirement is clear. Now, coming to, let's come by step. Okay, so first let's start with the top level. Okay, top level in a sense, the application level. Whatever the application we can see on our screen, right, in our PC, this is nothing but my application. Okay, so this application we are not going to build it anyways. This will be built using Python. Python tools or some kind of UI interface and all. Okay, so the buttons and the slide controller and all, everything will be created using some kind of Python code and all. Okay. Now, this whatever the user interface, whatever the user interface will be created, right? This will be linked to some other script. Okay, this will be linked to some other Python code. I will show you in the PPT. That will be basically it will be converted into some byte of information. Okay, so you can see over here. If I am going to select LED 1, here I can see the information or the byte which I'm going to have is going to change. This particular byte of information will be generated by my script which I'm going to write down. The software level script in my PC, it will be converted, and this particular byte will be sent to my FPGA. Let's say suppose if I'm going to select LED 2, then you can see it is changing. The byte is changing. Let's say if I'm going to select LED 3, the byte which I'm going to send is going to change. Okay, and let's say if I'm going to decrease the brightness, you can see in the brightness section, let me zoom in a little bit. You can see if I'm going to increase the brightness, the value which we are going to send it to my FPGA is going to change. And if I'm going to change the mode, the value which I'm going to send, it's an 8-bit data which I'm going to have, is going to change. Okay. So everything will be taken care in the software level, like what kind of byte should be sent if the user is sending fade, or if the user is clicking on static, what kind of byte should be sent to the FPGA, or if the user is sending LEDs, if the user is clicking LED 0, what kind of data information that should be sent to the FPGA, everything will be taken care in the software level. Is it clear? The second step, is it clear? So if the user is clicking some kind of button, or if the user is adjusting the brightness, or if the user is selecting static, dynamic, or something, then the information that should be sent by the sent to the FPGA will be decided by the software. Is it clear? Okay, so that is nothing but my second step. So whoever the end user who is using our application, they don't know what kind of code, or what kind of byte we are going to send to the FPGA, or what kind of operation, everything. They don't know anything. Just they are playing with this particular buttons, and everything is being reflecting on the FPGA. As an RTL design and engineer, we need to design few components that we are going to discuss. Okay. Now let me open this slide. Yeah. Now over here, we are going to, yeah, this is what I've said you. So we are going to have a host PC which is going to send a single byte serial commands over UART. Okay, and the FPGA receives, decodes it, and converts each command into a PWM signal that controls LED brightness entirely in digital logic with no external chip required. Now, what is going to happen? Let me open this particular board. So in this board, where is this? Yeah, this one. You can see that this is nothing but my USB host. So whatever the PC we are going to work with, right? So this PC will be connected to this particular UART interface. Okay, we are going to basically connect it with my UART interface. Now we are going to have something known as okay, this is basically USB. This is not UART. We are going to connect our PC with this particular USB interface. Now, whatever the commands which we are going to receive via the USB interface, that will be converted into UART protocol by some IC which I cannot find over here. Okay, there will be some kind of bridge which will be present that will be converting my USB into UART. Okay, so let me write it, draw it over here. So whatever the commands which I'm going to get it from my PC, whatever the byte information which I'm going to get it from my PC, that will be received by the USB interface, and there will be some kind of bridge which will be present that is going to convert your USB commands into UART commands, and this UART commands will be given to your actual FPGA. This is the data flow which we are going to have. So in the PC, let's say if I'm going to adjust this particular LED to LED 1, then what is going to happen? The command which we are going to send is this. This command will be sent by my PC to the USB, and from the USB it will be converted into UART, and it will be given to my FPGA. So this is what the data which we are going to send. This is a data flow which I'm going to have. Is it clear for everyone? The third step. Step number 3, is it clear? Okay. So what is happening is, let's say if I'm going to select LED 0, LED 0, you can see the command which I'm going to send to my USB or my board is this command. That is nothing but my data. And if I'm going to select fade, this is the data which I'm going to send my FPGA, and blink, this is the data which I'm going to send it to my FPGA. And if I'm going to adjust this particular brightness, this is the data which I'm going to send it to my FPGA. So this will be taken care in your software level. So you don't need to worry about how we are going to write down the code for adjusting this particular data and all. Okay. Is it clear, Jay Kumar? Now, let us first of all try to understand the meaning of each and every particular command. Then then we will able to understand what is happening over here. Okay. So we are going to have, let me open the PPT. Yes, this. So the user or the developer of software code, they are going to have this particular command reference where they are going to have, let's say, suppose if they want to adjust the brightness of their of the LED. Okay, so they are going to have basically 8-bit frame. So in the 8-bit frame, what they are going to do is the MSB bit they are going to adjust it. If it is equal to 0, then it is turned off completely. So you can see over here in this particular here also, if the brightness is completely 0, you can see the MSB bit is set to 0. If the brightness is increasing, then you are increasing this particular remaining bits. Okay, MSB will be 0 only. Okay, so whatever the 8 bits you are going to send, right? So in this particular 8 bits, the MSB bit is going to select what is the mode. For example, if you are dealing with your static, so here static is going to have the MSB bits as 1 0. Let's say suppose if you are going to deal with LED, LED has MSB bits as 0 1, and mode selecting has MSB bits as 1 0, and brightness setting has MSB bits 0 0. Okay, so using this particular MSB, I'm going to decide what is the configuration I'm going to have, whether I'm configuring brightness or whether I'm configuring LED or whether I'm configuring mode. Okay. So let's say suppose if I'm going to configure my brightness, then how hardware come to know that user is configuring brightness? It is going to refer to the MSB, which is 00. Now, how hardware will come to know user is trying to configure mode, that is static, fade or blink? It is going to refer to the MSB 10. How the hardware coming to know that the user wants to select an LED? It is going to come to know with the MSB 01. Let's say if the MSB is 01, the hardware will come to know that okay, the user wants to configure the LED, so it will be prepared in that particular way. Let's say suppose if the MSB bit is 10, then the hardware will come to know that okay, the user wants to set the mode, it will adjust itself like that. Let's say suppose if the MSB is 00, the hardware will come to know that okay, the user wants to play with the brightness, it will configure in that particular way. Is it clear, guys? How the hardware is basically trying to know what kind of configuration the user wants to. Okay. Anyone having any queries in this? Okay, great. Now, so coming over here, let's say if my byte is equal to 00, that means all the 8 bits are equal to 00. You can see if the brightness is being decreased, let's say if the brightness is completely decreased to 0, you can see the remaining byte of information 1, 2, 3, 4, 5, 6. All the 6 bits will be equal to 0. Okay. Now, let's say if the information the user is going to send is 40. Sorry, what happened to this? One second. Yeah. So this is what I was discussing about. So if my byte is basically 00, then I want to play with the brightness. Now it is basically 6 bit value from 0 to 63. Let's say suppose if my where is this one? Yeah. If my byte which I'm going to send is 40, then I'm going to have 25% brightness. Okay. So let's say if the user is setting the brightness as 40, hexadecimal 40, then I'm going to have basically 25% brightness. Let's say if the user is sending byte as 80, then I'm going to have 50% brightness. And if the user is sending this particular byte of information as C0, then I'm going to have the 75% brightness. And if it is completely all ones, all the 6 bits are equal to 1, then I'm going to have 100% LEDs completely bright. Yes, Jaykumar, I've already told you, right? We are going to discuss about entirely about UART protocol. First, I'm explaining how the project is working, how the user is basically creating the commands and all. Okay. Okay. Others, is it clear? How we are basically configuring the command and all? Okay. So I just wanted to give you an overview of how we are basically framing the command. Okay. Anyways, we are going to again come to this particular slide and we are going to discuss, but I wanted to give it in a first position only because we will have some key interest to learn what is happening over here. Okay. Yes. Now, so that is what we are going to do. So the PC is basically going to create a command, which is basically whatever the data information which we are going to send via the PC to the hardware is 8-bit basically, where MSB is basically of going to configure what kind of thing or operation which I want to do. And next is payload. Okay, so whatever the information I'm going to have, this is nothing but my payload. So that will be received by my hardware. Okay. And after hardware going to receive this particular 8-bit of data, it is going to decode the command. Okay. How it is going to decode the command, we are going to discuss. And it is going to generate the PWM signal and it is going to implement it on the hardware. Okay. Now, so if the user is going to click or he's going to drag the brightness, it is going to affect in the UI, where we can use this particular software which is known as Kinter or Web, and then that particular UI operations which we are going to do is that will be converted into a script which is basically PySerial builds the command byte, and this will be done in your software level. Okay, that we are not worried about it. Now, this particular byte of information which we are going to frame, right, that will be given to your USB of your FPGA. And in FPGA, we are going to have a bridge which is going to convert this USB to UART protocol. And our whatever the FPGA we are going to have, whatever the Verilog code which we are going to write down, right, that it is going to receive this particular commands via the UART protocol. It is going to receive via this UART RX, and this is going to give it to the decoder module, and decoder is going to decode this particular command, and it is going to implement on our LED. This is our particular project. Okay. So the flow is clear for everyone? We haven't started with anything. Just we are still in the flow of operation. That's it. What if we know the flow, then we can work on something. Okay. Just we have started with the flow itself. That's it. Okay. Now, so this is what you can the script is going to have in the Kinter. So this once you can Google it like how the software level coding is going to look like and how you can integrate with this. So it is basically going to detect whatever the events which are going to have in the UI level. And next it is going to run the Python code in the callback, and it is going to construct a particular byte of information, and then it is going to send this particular byte to our COM port, that is my USB port, and USB port it is going to receive whatever the FPGA which have, right, that is going to it is going to receive the byte, and it is going to convert it into UART frame, and it is going to give it to our hardware, that is nothing but my FPGA. Okay, so this is what the flow is going to look like. This you can once look into in Google or something if you want to explore the software level code also, like how exactly the Python code is being built and how the UI and the Python code are being working in the software level. If you want to explore, you can explore it. But this particular workshop, we are focusing upon the hardware level things. Okay. Now, so this is what we are going to have. This is the PC terminal, which it is sending the byte of information, and we are going to have the UART receiver, which it is receiving the bytes. And from here, we are implementing it on our FPGA. Okay. So this is basically sent to the USB, and USB it is sending to our bridge, and bridge it is sending to our RX pin, RX pin of our FPGA. Okay, so FPGA we are going to have whatever the FPGA pin we have, right? So we are going to have one RX pin. The bridge is basically sending this particular UART command to this particular RX pin. That is nothing but my UART receiver that we are going to develop in our Verilog. And after receiving this particular byte, we are going to forward it to our command decoder, where it is going to decode what exactly the command is. Let's say if I'm going to send just simply 00101011 without discussing anything, and I've told you 0010111010, what is it? So you need to decode it, right? You need to have some kind of logic which can able to decode what is the information which is present. Then only you can do something, right? So that is what we are going to have, which is nothing but my decoder. Next, we are going to have something known as LED controller, which is going to control my LED blinking and all. We have, right, that it is going to control my LED. And next, we are going to implement it on my physical LED. This is what I'm going to have. So we are going to have something known as UART RX and the command decoder, which is going to interrupt the RX data as command. What is the brightness? What is which particular LED should we select? That and all. This command decoder is going to decode. And LED controller, it is going to control the brightness. It is going to generate a PWM signal. And next top model, it is going to instantiate all these particular modules. And UART-TX and FIFO, we are not going to implement it now. We can implement it in our future workshops. Okay, first let's implement this particular things. So this is about our particular project idea and what we are going to implement. If this is clear, we can move forward, and once we can discuss about UART protocol and the baud rate and other kind of things. So is this clear? Any doubts or any queries over here? Okay, that's great. Now, first of all, without knowing UART protocol, we cannot proceed with this particular project. So let us first of all try to understand what do I mean by UART protocol. Can anyone tell me what do you mean by UART protocol? What is full form of UART? Universal Asynchronous Receiver and Transmitter, right? And one second, I've got some query in YouTube also. Ritesh, once you can explore like how UI and the Python script are going to connected, and via some putty terminal, if you have heard about it, we are going to basically transfer that particular byte of information via the USB. Okay, this is I got query from YouTube, so I'm answering to them. Yeah. And UART protocol comes under APB or XA. No, it's a separate protocol, Mr. Killer in YouTube. So I'm answering those particular queries. Okay. Coming back to Meet answers. Yes, universal asynchronous receiver and transmitter. Now, what do you mean by asynchronous over here? So you're answering that it is asynchronous, right? So what do you mean by asynchronous over here? You can also unmute your mic if you want. So consider this as your excellent opportunity to speak up. No common clock between the transmitter and receiver. Okay. In our project, who is master and who is slave? Whatever the project which I have demonstrated now, right? So who is the master and who is the slave? Anyone wants to answer? Who is the master and who is the slave? Exactly. Master is a software and slave is a exactly. Yes. Because master is basically creating the commands and it is basically sending everything and it is initiating the transaction. Okay. So as of now, in our particular project, we are going to have master as our software and slave is nothing but my RX or my FPGA, right? Now, can you here asynchronous in the sense there is nowhere my particular master. Okay, here master can also be my bridge, which is basically between my USB and my the RTL code. Okay, that is acting basically as my master. So nowhere the bridge is sending the clock information to my RTL. Okay, so that's the reason we are going to consider this as asynchronous in nature. Okay, so what I'm speaking is, so over here we had a USB interface and we had a bridge, and this bridge is basically sending the data to my RTL. Okay, that is nothing but my FPGA and the RTL code which we have developed in our FPGA, right? So this is having a RX pin, and this is nothing but my bridge. And this bridge is basically sending the data to my RX, and this is my USB interface. And via this USB interface, the data is being sent to my bridge. And obviously, these are going to work with some reference clock, right? So nowhere the bridge is basically sending the clock to my RTL. Okay, but RTL is also going to have the same reference clock. Okay, so asynchronous in the sense, so bridge is not basically sharing the clock to my RTL. That is nothing but my asynchronous in nature. Okay, but RTL is also going to take the physical clock which is being present over here. Okay, using this particular clock, we are going to generate our own clock kind of thing, and we are going to sample the data. Okay, we are going to have something known as baud rate. That is the reason UART is basically asynchronous in nature. Is it clear? Whereas in your SPI or I2C, if you have observed in your SPI, whatever the master is there, that is basically sending the clock with respect to the data also. That's the reason it is synchronous in nature. Yes or no? Okay. Now, can anyone tell me? Okay, it is asynchronous in nature. Fine. Then how we are going to synchronize my master and slave? Because UART protocol is not going to deal with high frequency clock. Then how we are going to synchronize them. Exactly. We are going to use something known as baud rate. Now, what do you mean by baud rate? Anyone wants to answer? What is the full, what is formula, or what is the definition of a baud rate? What is a baud rate, and anyone wants to answer? Like, what is a baud rate? Bits per second. Exactly. So basically, baud rate is nothing but symbols per second. Okay. And here in the UART protocol, it's nothing but one symbol is going to have only one bit, so it's nothing but bits per second. Now, what is going to happen is, let me show you over here. So whatever the bridge we are going to have is USB to UART bridge. This particular bridge can also be configured. Okay. How we are going to configure via the PC using the Python script only. I'm going to configure the baud rate of this particular bridge. Okay. So let's say the bridge is going to, I'm going to configure it to work it with 9600 baud rate. So what is the bridge is going to do? It is going to send the data onto this particular TX line with this particular baud rate, and receiver is also going to work this particular baud rate 9600 only. Okay, so that both will be synchronized. This is what we are going to do for synchronizing both of them. Okay, is it clear, guys, how we are going to send the data and all? Yes. So over here, via the USB protocol, the data will be getting at higher speeds, but over here, the bridge, it is going to basically cannot send that particular data with that much of higher speeds. It is going to basically use this particular 9600 baud rate, and it is going to give it to my RTL. Okay. Now, first of all, let us try to understand what do you mean by baud rate, and how it is playing a key role in establishing our communication. Then, if it is clear, then we can move forward. Now, basically, let's say if my clock frequency is around 50 megahertz. This is my clock frequency, let's say. Now, I'm going to have this clock frequency for sending my data. Okay, let's say if I'm going to simply write down a Verilog code like always at the rate passage of clock, something like this. Data underscore out is equal to some reg underscore data. It's a completely random code I've written over here. So what is happening over here? At every particular passage of clock, I'm going to send this particular data to my data underscore out. Let's say I'm going to send one bit of data over here, and the second clock edge I'm going to second bit, third bit, fourth bit, like this I'm going to send the data over here. And this clock frequency is over here 50 megahertz. Now, what is the bit time we are allocating over here? Anyone wants to answer? What is the bit time over here? That is the time which we are allocating for one particular bit. What is the bit time over here? Let's see who can answer this. If the clock frequency is 50 megahertz, and this is my code, and this is the requirement which I'm going to have, then what is the bit time which we are going to have over here? 20 nanoseconds. 1 by 50 megahertz is nothing but 1 by 50 is nothing but 20 nanoseconds. If you calculate, you are going to get this. That means this particular cycle is basically having 20 nanoseconds. That means for one bit, you are allocating 20 nanosecond. Okay. Now, let's say if we are going to work with this particular frequency only. Let's say if I'm going to work with this particular frequency only, and let's say the bit time I have allocated is 20 nanosecond. That means, let's say this reg underscore data at first cycle it is equal to 1. At first cycle, this reg underscore data is equal to 1. And second cycle, this particular reg underscore data is equal to 0. And third cycle, it is equal to 1. Fourth cycle, it is equal to 0. Fifth cycle, it is equal to 1. So this is the reg underscore data information which I'm going to send for every cycle. You can see this is basically toggling for every particular cycle. It is 1 and it is 0, it is 1, it is 0, it is 1. Like this, we are going to have the toggling information. Let's say this particular data, it is being assigned to data underscore out, and this is nothing but my physical LED I'm going to have. Now, what do you think? Am I going to see any particular toggling onto this particular LED or not? If this is the case, I'm directly connecting my 50 megahertz and I'm driving it into my data underscore out, which is nothing but my physical LED. What do you think? Can I see any particular toggling effect on my LED or not? Yes or no? Why no? Okay, others also try to answer. Can I see any particular toggling mechanism which I can observe on my physical LED or not? Is the question. It can be visible, right? I'm simply driving 101010. My LED can also blink like 1010. Yes or no? Exactly. So 20 nanosecond, you are basically allocating for one bit, you are allocating 20 nanosecond, and your eye cannot capture this small amount of time. Okay. Basically, your eye is not able to capture this small amount of time. Am I right or wrong? Yes or no? So if you have FPGA with you, you can basically try this particular thing. You can just directly connect it with this high clock frequency and you can check it out. You cannot observe this particular blinking at all. Okay. So, and this is LED is one of the peripheral. So, generally, if you are working with any of the peripherals, you cannot deal with high frequency clocks. Okay, you cannot directly connect to a high frequency clock, and you can work with it. It may be any particular peripheral you're working with. Peripherals are meant for working with lower frequencies. Okay, so like peripherals like keyboard or a particular kind of sensor or a particular kind of LED, you cannot work with high frequency clocks. So for bridging this particular lower frequency peripherals and your high frequency processor, this is where we are going to use our UART. Not only with your LED, if you are working with some kind of sensor or if you are working with some kind of display kind of thing, you are going to use UART protocol because UART is designed to work with lower speed frequency, I mean lower speed peripherals. Is it clear why we are using UART over here? Okay. Now, so over here, let's say that's the reason I'm going to use a concept of baud rate over here because UART is not designed to work with this high frequency. I need to have some kind of thing which is known as baud rate. So baud rate also, let's say if I'm going to have a baud rate of 9600, let me write it down in the next slide. So let's say if my baud rate is basically 9600, which is nothing but my symbols per second. Okay. Symbol, basically one symbol is having only one bit as of now. So I'm going to have only one bit per second. So basically I need to send one bit per second. So this one bit per second is nothing but my bit rate. Generally the formula for your bit rate is basically one bit per second. That is nothing but my bit rate. Okay. So in the case of my UART protocol, baud rate is basically equal to bit rate. Okay. Now I have a bit rate of 9600. What do you think the bit time, which is nothing but a reciprocal of bit rate? What do you think? 1 by bit rate, which is 1 by 9600. Can anyone calculate this and let me know what is the bit time you are going to get for this particular 9600? Not regulating, it is basically bridging. Okay. Okay. What is the bit time over here? Okay, if you convert it into microsecond, it will be around 104 microsecond. Am I correct? If you are going to convert it into microsecond, that is 10 power minus 6, it will be around 104 microsecond. Okay, so this will be around 104 microsecond. That means you are basically allocating 104 microsecond for every particular bit. So if this is your clock, so for every particular bit, you are going to allocate 104 microsecond. But previously, what was happening for every particular bit, you are allocating only 20 nanosecond, which was very, very, very higher frequency. Okay, that means it's very lesser time. For one bit, you are allocating very, very less time. But over here, you are increasing the time which you are allocating for one particular bit. Okay, this is what baud rate means. Is it clear for everyone? What do you mean by baud rate? So generally we study baud rate, but we don't know what is it actually doing. Okay, this is what baud rate means. Baud rate is basically you're increasing the time period for a particular bit. Okay, that is nothing but my baud rate. Let's say suppose if this time you have allocated for a particular bit is too longer, then you increase the baud rate. Okay, what happens if you are going to increase the baud rate? If bit rate is increasing, then what about the time? Time is going to decrease or increase? If bit rate is increasing, what about the time? The bit time you are going to allocate, is it going to increase or decrease? Exactly. The time you are going to allocate for a particular bit is going to decrease. It depends again. It depends upon the when you're working with your UART protocol, the sender and receiver is going to adjust. You need to check it out, like for what particular baud rate the communication is being established and the data is being transferred. It depends upon the while you are working with it. Okay. Now let's say suppose this is the case which we are going to have. And okay, first of all, tell me baud rate, is it clear for everyone? So if you have seen baud rate anywhere, what do you mean by baud rate? Can you able to visualize it? Okay, fine. Now, how to implement this in our coding? So anyone wants to answer how we are going to implement this? But in this case, what is the lower frequency peripheral? Exactly. So peripheral, we need to deal with lower speed, and processor is dealing with your higher speed. Not processor, we are not actually having a physical processor. We are having basically, the host or the PC. Here in Nexus, this FPGA, we don't have a processor. We are basically sending the data from our external PC. Okay. PC is basically sending the bits with respect to high speed clock, but not the processor. Here we don't have any physical processor which is present on this particular board. Yeah. So is the baud rate concept, is it clear for everyone? Shall we move forward? Okay, great. Now, how to implement this particular baud rate? How to implement this particular baud rate in our Verilog coding? Let us try to understand this. So, if I'm going to receive the data, so let's say if this is my code, let's say this is my UART receiver code. This is my UART receiver code where at every passage of clock, I'm going to sample the data. Let me write down a simple code. So always at the rate passage of clock, I'm going to simply write down rx underscore n is equal to data underscore n. So this is the receiver code which I've written. This is my receiver code. Now, is this going to work? This is my 50 megahertz clock. If I'm going to receive the data with respect to 50 megahertz clock, then is this particular code going to work? Yes or no? Is this code going to work? Obviously, no, right? It's not going to work because the frequency here is 50 megahertz. Okay. And data in is basically given by my transmitter, which is having a particular, 50 megahertz is nothing but 20 nanosecond time period, where my transmitter is sending the data with respect to 104 microseconds. Okay. So in receiver, just I've written Rx is equal to data in, but in the receiver, we are going to have some kind of FSM where I'm going to have some start state and data and parity and stop state. Like this, I'm going to build an FSM. I will show you. So this particular state transition should be happening with the time of 104 microsecond. Then only I can able to receive all the particular data items. But if this particular state transition is happening for 20 nanosecond itself, how you are supposed to receive all the particular data? By then, the transmitter is going to send you another bit of data. You might have ended the transaction itself. Okay, this is the major thing we are going to figure it out. Okay, is it clear? So whatever the RX logic which I'm going to write down, I'm going to use an FSF, the state transition, where I need to sample all the particular bits of data. If the reception is happening with a very lower time period, the transition is happening for every 20 nanosecond, then I'm not going to receive all the particular data. Why then, if I'm going to receive the second bit of data, I might be entering into the stop state and ending all the particular transaction. Okay. Now I need to control this. How I'm going to control this particular flow of operation is I'm going to use a counter. Okay. So I'm going to basically have a counter which is going to count for some number of cycles, which is known as divisor. And if this particular count has reached, then I'm going to enable Rx underscore enable. Then if it is given, then I'm going to have the state transition from start to data. And if again this Rx enable is made to 1, then I'm going to sample another bit of data. This is data 1. Next, I'm going to sample data 2. Next, I'm going to sample data 3. Like this, I'm going to sample all the 8 bits of data with respect to this Rx enable. Okay, this is what I'm going to do. Now, what should be this particular divisor value? Let us try to calculate. Okay, so how to calculate this particular divisor value? Counter is going to basically count the number of cycles. You don't know what is the value and all. Uh, what is your question, Divya? Okay, let me reframe it again. So in RX logic, we are going to develop some kind of FSM. So, okay, before that, we will discuss about the UART frame first. So without discussing UART frame, it will be difficult to understand the things. Okay, first of all, can anyone tell me what is the UART frame it is going to contain? What are the different things we are going to have in our UART frame? What are the different kind of fields which we are going to have in our UART frame? Can anyone tell me if you know? Start bit, data, parity, and stop. These are the this is my UART frame. So whatever the bridge we are going to have is it is going to set this particular frame. This is my start bit and this is my data. Let's assume it is 8 bit. And next is parity and next is stop. So this is a frame which my bridge it is going to send it to my RTL code. Now, whether it is sent in parallel format or serial format, whether the entire frame will be sent at a time or whether this particular frame will be converted into bit format and it is going to be sent serial format. So this particular frame, first of all, it will be converted into serial format and this will be sent one by one. Okay. Now, first the start bit will be sent. This is basically of 1 bit. This is 8 bit and this is 1 bit and this is 1 bit. So this will be sent bit by bit. Okay. Now, first the start bit will be set. Now, if I'm going to develop the Verilog code for my UART RX, I'm going to use something known as FSM. Okay. So in FSM, I will show you in great detail. So in FSM, I'm going to have something known as start state. And then I'm going to a state which is known as data state. So in the data state, I'm going to receive all the 8 bits of data. And next, I'm going to have parity state. Next, I'm going to have something known as stop state. And then I'm going to start state again. Now, how to write this particular code? If you know Verilog coding, how to write down FSM coding, you might have seen this particular thing. Always at the rate passage of clock, we are going to basically write down our state logic, which is nothing but present state is equal to next state. And next, we are going to have the next state logic, which is basically a combinational logic. Always at the rate, let's say, always at the rate star, which is a combinational logic, right? So when is my transaction is going to start? Can anyone tell me how receiver is going to come to know whether a particular transaction has started? When start is equal to 0. So that is what I'm going to write down over here. Start is equal to 0. Then my next state is equal to uh, data. Else next state is equal to Okay, here I'm going to write down my case of present state. Okay, so depending upon my present state, first I will be in the start state. Next, I'm going to my data state. Now, I have entered into my data state. Now, what I'm going to do over here, if bit underscore count is equal to 8, next state is equal to parity, else next state is equal to data only. Why I have written bit underscore count is equal to 8? That means I have 8 bits of data, right? This is my actual data, right? If bit underscore count is equal to 8, then I'm going to enter into parity, or else still I'm receiving the data. Okay. And remember, this data is sent by the bridge with a time period of 104 microsecond. That means every bit is having this much of time period, or the frequency is 20 nanosecond. Now, can anyone tell me where to write this bit underscore count decrement, like checking logic? Where should I write down? So bit count will be initially 0, next it will be 1, next it will be 2. So, okay, up to 7. We are counting from 0, right? 0 to 7 is 8. That means we are basically checking whether we have received all the 8 bits of data. If we have received all the 8 bits of data, we are moving to data state. Now, where to write this bit count logic? Whether I can write it down in my combinational logic. Okay, before that, is this code clear? I think this is a basic code, right? So I'm going to check for my start condition. Next, I'm going to data state, and in the data state, I'm basically checking whether I have received all the 8 bits of data or not. If I have received, I'm going to parity, or else I'm going to stay in the data. Is this code clear? First of all, tell me. This is a basic simple code. Just by seeing the logic, I've written this particular. Okay. Now tell me where to write this particular bit count incrementing logic. We should increment it, right? So bit count is equal to bit count plus 1. Where should we write it down? Whether in the combinational logic, or whether in the sequential logic, or whether with respect to some clock, where should we write this particular bit count incrementing? We should basically check, right? After getting each and every particular data, we should check it, right? So obviously the counter logic should be written in the sequential logic. Am I right? Yes or no? So I cannot write it over here now. So next state is equal to data. Bit count is equal to bit count plus 1. I cannot write it down over here because it's a combinational logic. Okay. So either I should write down in my passage of clock. So what I'm going to write down here, if present state is equal to data, then bit count is equal to bit underscore count is equal to bit underscore count plus 1. With respect to clock, I should write down this particular counting. And here I am assuming that for every passage of clock, I'm going to get the data, right? Now, what is the clock frequency I took over here, which is 50 megahertz? That means it is basically what is the time period, which is 20 nanoseconds. That means I'm assuming that for every 20 nanoseconds, I'm getting a bit and I'm incrementing it. So what is going to happen after 8 cycles? 1, 2, 3, 4, 5, 6, 7, 8. That means 20 into 8, which is basically 160 nanoseconds. After 160 nanoseconds, my bit count will be reaching the value of 7, and just I'm going to enter into parity. Now, can anyone tell me whether I'm able to receive all the 8 bits of data or not in this particular code? Let me repeat my question again. So for one cycle, I'm allocating 20 nanosecond. I'm assuming that in 8 cycles, I'm going to get all the 8 bits of data. That means here my time period is 20 nanoseconds. That means 20 into 8 is basically 160 nanoseconds. So after 160 nanoseconds, my bit count will be equal to 7, and I'm entering into parity state. Now tell me whether I'm able to receive the data or not, all the 8 bits of data or not. If I'm going to basically change from 80 nanos. No, here, what is the transmitter sending? What is the transmitter using the time period for each bit? Where is the transmitter? This one. Transmitter is, what is the transmitter allocating for each particular bit? It is, for each bit, it is allocating 104 microsecond. Where is 104 microsecond and where is 80 nanosecond? Within 80 nanosecond, you are assuming that you have sampled 8 bits of data and you are moving to next state. But transmitter is still taking 104 microsecond for transmitting a single bit. Now tell me whether you are able to sample all the 8 bits of data. Transmitter is taking, for one bit, it is taking 104 microseconds to send. But receiver, we are assuming that we are getting the data within 8 cycles. That is, 20 into 8 is 160 nanoseconds. And we are just entering into the next state, assuming that we have received all the data. But is it happening so? No. Is it clear for everyone? So this is very, very important in terms of interview also. So like not only writing the code, we need to understand what is happening in terms of timing. Okay, this is very, very important thing to be understood. Okay, so what is it we are going to do? That is what we are trying to do. We need to wait for, in our receiver code, we need to wait for how many nanoseconds now? Can anyone tell me? Or how much time we should wait for sampling my one bit of data? How much time I should wait? Yeah, cycles, okay, but I'm asking time. How much time I should wait for receiving one bit of data? 104 microseconds. I need to wait 104 microseconds for receiving one bit of data. So for receiving 8 bits of data, how much time I should wait? 104 into 8. 104 into 8, how many microseconds is it? So can anyone calculate and tell me? 104 into 8, which is 832 microseconds. You need to wait, and then you can see that you have received all the data. But over here, just waiting for 80 nanoseconds and you're transitioning into the next state. How can you sample 8 bits of data? Okay, so for that, we are going to use something known as baud rate controller. So this baud rate controller is going to give you some kind of enable signals which it is going to control. You're going to basically wait for this number of microsecond. Now that we are going to have the calculation. Is it clear now for everyone? Okay. Now what we are going to do, so let me erase this. I hope now the code is clear. So if you are learning anything, any particular code, please be mindful about the timing and everything. Okay. Now, so we need to figure it out, that we need to basically wait for 104 microsecond, right? Now, we cannot simply write hash 104 clock is equal to not of clock. No, we cannot use hash operator because it is not synthesizable. So we are going to use a counter. So counter is going to basically count some number of cycles, and then it is going to provide some signal which is known as enable. And if this particular enable signal is made to 1, then we can sample next bit of data. And again, if this enable is made to 1, we can sample another bit of data. So that we are going to calculate. That is nothing but my divisor, which is basically equal to, this is nothing but my number of cycles, which is nothing but time into frequency. Frequency is nothing but my the reference clock, which is 50 megahertz, 50 into 10 power 6. And what is my time? Bit time is basically 104 microsecond. So I can reciprocate it as 50 into 10 power 6 divided by 9600 will give me the number of cycles I am going to take for transmit a one bit of data or for receiving a one bit of data. Now, can anyone calculate this and tell me 50 into 10 power 6 divided by 9600? So here what I'm finding out, I'm basically finding out for one bit of data, for achieving this 104 microsecond, how many number of cycles I need to wait. This is what the formula I'm going to use. Divisor into time into frequency. Time is 104 microsecond and frequency is 15 to 10 power 6. So what is that we are going to get? 50 into 10 power 6 by 9600. Can anyone calculate and tell me? Exactly, 5208 cycles. So if you need to allocate 5208 cycles. So if you are working with a 50 megahertz clock, then you need to wait for 5208 cycles. Then you are sampling one bit of data. This is what our conclusion. If we are basically working with 50 megahertz clock, sorry, not 50 mega, yeah, 50 megahertz clock. This is my frequency, then I need to basically wait for 5208 cycles for receiving one bit of data. Is it clear for everyone? Let's say, suppose if I'm going to allocate only, let's say if my bit time is basically 20 nanosecond, then what is the number of cycles you are going to allocate? So cycles is equal to time into frequency. 20 nanoseconds into 50 megahertz, which will cancel out each other, and you are going to allocate one number of cycle. That is what we are going to do now. If we are going to have bit time is equal to 20 nanosecond. But what is our requirement? Our requirement is bit time is basically 104 microsecond. Then what is the number of cycles you are going to allocate for one number of bit is nothing but 104 microsecond into 50 megahertz, which is giving us 5208 cycles. So that you need to wait for 5208 cycles for sampling one bit of data. Here also one bit of data. If you are allocating 20 nanoseconds for one bit. Here, if you are allocating 104 microsecond, you are going to have 5208 cycles. This is how we are going to calculate it. Is it clear? Others, is it clear? So this is a very, very important calculation to be understood. This is where it's very confusing and people neglect it. This is what interviewers are going to expect from you. Because this is a core logic, which is basically we are doing, and it's a duty of an RTL engineer to design it. Okay. Yeah. Now, so we are basically having 5208 cycles. That means I'm going to allocate 5208 cycles for one particular bit. This is what my baud rate generator model is going to do. So I'm going to develop a counter if it is reaching this particular divisor value. I'm going to make this enable is equal to 1. If this receiver, we had an FSM diagram, right? Always at the rate passage of clock and all. Always at the rate passage of clock. If this enable is equal to 1, then we are going to have the transition and we are going to have this, the what was the variable which were declared over here? I think I've erased it. Okay. Bit count is equal to bit count plus 1. Bit underscore count is equal to bit underscore count plus 1. This is the logic which we are going to develop. That means we are basically assuming that that particular bit will be available for this much of time. That is nothing but my 5208 cycles. This I will anyways, I will show you in the code. It will be more clear. Yes. So is it clear for everyone up to here? Any doubts or any queries over here? Great, great. Okay. So this was the main core logic that we need to understand when we are implementing UART receiver. Yeah. So when we are implementing our UART receiver, this is what we need to have in our understanding. Rest all things is very, very simpler and easy. The midpoint sampling and all. Anyways, the coding part we are going to start in our tomorrow session, and we are going to start our discussion how to develop the code from the top to bottom and how we are going to control our LED. And let's say if tomorrow time doesn't permit, like I'm allocating like 1 hour of time. Let's say if 1 hour of time is not sufficient, then we are going to have the next session on next weekend. Okay. So that's about this particular session. If you have any doubts or any other queries you wanted to discuss, you can discuss with me, or else we can wrap up this session. Okay. Thank you. Thank you for your time and thank you for your patience. Thank you.
Thank you, sir.